Hi, this is Mrs. Villette, and this is a quick video to introduce our definitions for increasing and decreasing functions. We're going to start with a function that is defined on an interval I. So that just means that its domain is a subset of that interval. Not necessarily that the function is continuous, but just that it has a function value for every x value in that interval. Our definition for an increasing function is that f is increasing on this interval I if for every a less than b in I, f of a is less than or equal to f of b. We probably have an idea of what this looks like, but we're talking about on our interval we have a, b, and if we have our f of a right here, then in order to be increasing for any two such points, a and b, where a is to the left of b, then my f of a has to be less than or equal to my f of b. So we could either be here, or we could be a little bit higher, and then our function would still be increasing. Now our definition of decreasing is just the opposite. We're still assuming that a is to the left of b. We're just saying in this case the f of a is greater than or equal to the f of b. So we're just going down or staying the same. So the or equal to part is important here. We have a different definition for strictly increasing. So strictly increasing just removes that equal to part of the inequality. So f of a has to be strictly less than f of b. And similar for strictly decreasing. So just taking a look at a couple examples. So we have a function here, it's just a quadratic function. It's increasing from negative infinity to 1, and then it is decreasing from 1 until infinity. We don't really include that endpoint, although you can. This is kind of another place where we have these disagreements on what can happen at endpoints. So at 1, I would argue that the function is neither increasing or decreasing because we don't really have an understanding of what it means to be increasing or decreasing at a point. We only know what it means to be increasing or decreasing on an interval. So I could include this one in my interval, or I could not, and I would still be correct following these definitions that we have up here. Okay, this function's a little bit strange. This function is increasing on negative infinity to infinity. Our definition was just that the y values had to get larger or stay the same. So this part where the function is constant, that is technically increasing. Now this is strictly increasing. So we have this section right here where it's strictly increasing from 1 to infinity. And then we have this other section where it's just increasing. But you might say if it's increasing, well, isn't it also decreasing? Yes, it is also decreasing. So constant functions, this is important. According to this definition, constant functions are simultaneously increasing and decreasing. A better word to describe these functions would just be the word that describes them, which is they are constant. What we want to do in these definitions is allow a function to kind of momentarily level out and not have that interrupt the fact that it's increasing or decreasing. So here's where the calculus comes in. This is our test for increasing and decreasing functions. Now this does require that the function is continuous. So let f be a continuous function on the closed interval a to b and differentiable on the open interval a to b. If your f prime of c, so your first derivative, is positive for all c in the interior interval, then f is strictly increasing on the interval a to b. So notice the word strictly. We're talking about that actually increasing and going up rather than staying constant. Similarly, if my first derivative is negative, then the function is strictly decreasing. And if my first derivative is 0 for all c, then the function is constant in that interval. Now we can see this little footnote. The little footnote said that this also holds if f prime of c is equal to 0, for a finite number of values of c in the interval a to b. So we allow the derivative to be 0 at maybe just one or two instantaneous values. I mean, it says finite, but we're not saying that the function, that the derivative is 0 over an interval. We're just saying at a finite number of points. So if your derivative is 0 just at one or 2 points in the interval, we're still going to consider that to be strictly increasing. So the example that I want to do with you that actually uses calculus is to show that f of x, which is negative 1 over the cube of x, is decreasing everywhere it is defined. So it's important here that we say where it is defined. And I just realized that I thought I was fixing a mistake that I made, and it actually wasn't a mistake, and that should just be positive 1 over x cubed. In my head, I was thinking x cubed. Okay, so fix that, and then go ahead and we're going to go on with the example. The first thing that we need to do is figure out where is this function defined. So what is the domain? Well, the domain of 1 over x cubed is all x's that are not 0. So from negative infinity to 0, and then from 0 until infinity. Now, in order to use this test for increasing and decreasing functions, I need to find the first derivative. So f prime of x would be the derivative of x to the negative 3, which would be negative 3 x to the negative 4, or negative 3 over x to the 4th. We know that x to the 4th is always positive as long as your x is not 0. We don't even care if it's positive or negative. So as long as x is non-zero, x to the 4th is positive. So we can say negative 3 over x to the 4th is always negative so long as our x is not equal to 0. So our test was if the derivative is negative for all c in an interval, then the function is strictly increasing. My derivative is negative for all values of x except 0, and 0, notice, is the only number that is not included in my domain, so that means our f of x is decreasing on its domain, so everywhere it is defined.